Hey guys, so what we've got here is a bit of a guide on how to build a drum sterilizer, a bubble barrel, an atmospheric sterilizer, a super pasteurizer, whatever you want to call it. This is a bit of a guide on how to make them. Essentially, the principle is long periods of time at a constant heat will kill most contamination off. It will just stunt some, however, by the time that it becomes active again, you should have a thriving mycelium colony going. So, with that in mind, let's go over the principles of a steam sterilizer. As the name suggests, it uses steam to sterilize. So what you're going to need is a heat source. This can be through an element, or it can be through a gas burner, or it can even be through some kind of induction compatible device. So long as you're getting heat in your barrel, it doesn't really matter where it comes from. I've chosen an element. I think they're the more efficient type because the element is in direct contact with the water, so there's minimal heat loss, versus a gas burner, which loses a lot of heat in the transfer. You're also going to need a way of regulating the water. This can be as simple as topping up periodically using a sight glass, or you can have a float valve, which is the most common low maintenance way of doing it. These float valves have got to be reasonably hardy since the environment they live in is very, very hot. It's around 90 degrees, 95 degrees, so it's worth buying a decent float valve. Next, you're going to want to drain. This is obviously to get rid of all the water, but it's also to get rid of all the detritus that comes with the water. Your bags will tend to be covered in sawdust and other nasties that you want to get rid of. Otherwise, they'll stain your barrel, they'll look bad, and they'll be a future source of contamination if left for a long period of time. So just bear that in mind. Obviously, because we're generating steam and heat, we're also going to be generating pressure if we don't have a way of venting it. And I want to make this clear now, these aren't pressure vessels. You can get away with a little bit of back pressure, but pressurizing them is a bad idea. You'll stress the seams, they're not designed for it, and they're not tested for it. So just bear that in mind if you do decide to pressurize your barrel. What I use is a ball valve. This ball valve gives me a little bit of control, and it allows me to control the vent of steam. So I can and do create a little bit of back pressure, which does bump the temperature up ever so slightly. In the lid, I use a component which separates the top of the lid from the substrate bags. And this is in case bags inflate during sterilization. It's not the most common thing in the world, especially at these temperatures and pressures. However, it may happen. So my steam spacer, what that does is creates multiple points for the steam to escape rather than just one. So if the bag inflates, the single port won't be blocked. There's lots and lots of ports, and hopefully that will become clear as the video goes on. So there's all sorts of other accessories you can add to these. There's temperature controllers and things like that. We'll get to that in a later video and probably in a later blog post. However, let's begin the actual construction of it. You can make your barrel out of pretty much anything that's going to withstand long periods of high temperatures. However, for this purpose, I've chosen stainless steel. I've had a mild steel barrel for a long period of time and it's great. However, they do rust, they do leave rusty water there, and they're not the prettiest things in the world. Stainless steel barrels are great, however, they are incredibly expensive. So your startup cost with a stainless barrel is going to be approximately 10 to 20 times more expensive than if you're using a mild steel or even a galvanized steel barrel. So just bear that in mind. I had these laser cut. These are false bottoms made from 304 stainless steel. I'm going to be selling these in my shop reasonably soon. They're going to be pre-notched and designed for a 205 litre or 45 gallon drum. As you can see here, there's two slots cut out. One is for the heating element to pass through, and one is for the float valve to pass through, which is obviously for water regulation. As you can see, the little plate on top is for the steam to escape, and that will become clearer a little bit later on in the video. You can also see there that the single large plate that actually holds the bags doesn't need multiple holes in it for the steam to pass through, because it's about heat transfer as much as anything, and the steam will not only transfer heat through the bottom of the barrel, it will transfer it up and around the sides. And if you pack your barrel correctly, you'll actually encourage a little heat channel where steam can pass through and evenly distribute between the bags. I'm using a tri-clamp element. This is probably the most common element in the home brewing world, therefore there are a lot of them out there and there's a lot of choices. I chose to go with a worldless bulkhead kit. What that means is the nut, the tri-clamp fitting and the O-ring are one piece. You essentially clamp the worldless bulkhead fitting onto the barrel through a hole that you make, and that creates a watertight seal for you to then attach your tri-clamp ferrule to. I went for a 1.5 inch ferrule and a 1.5 inch element. This is because there's a lower profile, meaning I didn't have to have as much water in the reservoir as if I went for a 2 or a 2.5 inch. It's not really a big deal because the bigger the element, the more water that your element is going to be able to heat, so it's kind of relative. However, for the size barrel that I have, I thought 6, 7, 8 kilowatt elements were a little bit over the top. Here you can see the float valve and the drain that I've got. It's essentially cobbled to bits from things I've got lying around the garage. However, it's all 1/2 inch BSP, all stainless steel, and all sealed with O-rings and gaskets to create a watertight seal. These aren't expensive, they are a bit of a pain to get hold of, so keep an eye on my blog, keep an eye on my shop, because I will have a kit for sale in the near future containing everything you're going to need to make your own, regardless of if you use mild steel, stainless steel, galvanized steel, or any other kind of steel for that matter. Here we've got a PID controller for controlling the temperature. It's called a PID controller and it stands for a proportional integral derivative. Don't honestly know what that means. It's used in automation quite a lot, but essentially the components inside that learn and figure out when and how to turn on your element to keep the temperature you have set. That may sound exactly like a thermostat. However, a thermostat is on or off between a range, whereas a PID controller constantly changes depending on the temperature. Quite fascinating things to read about and watch videos on, but I won't go into too much detail in this video about them. But that's enough talking about components. This is how I put it all together. I started with an A4 piece of paper taped end to end. This way I had a template. So what I did next was draw a line across the bottom of the paper. This represented the bottom of the barrel. Barrels generally come concave. This means that the barrel is domed upwards and inwards. So if you were to use the bottom of the barrel as your datum, you would not be able to secure the nut on because you would foul, as when you rotate a hex nut, the point or the crest of the hex will catch on the bottom of the barrel. So you need to give yourself a margin of error, otherwise you will run into difficulties. This can be an expensive mistake, especially with a stainless steel barrel. It's always easier to measure from the inside of the barrel rather than the outside. That's because the inside underside of the barrel is actually sitting higher by about 15 millimeters than the outside of the barrel. It sits on a rim, essentially, so bear that in mind when you're doing your calculations. I find it much easier to start with a template. So what I did, like I said, is tape 2 pieces of paper together end to end. I measured 5 millimeters up from the bottom of the paper. That 5 millimeter space represents the bottom of my barrel. Using some maths that my friend figured out for me, I found the middle of what I believed to be would be the false bottom. As you come out from the false bottom, obviously the angle increases, therefore the spacing increases between the holes. So with the maths that my friend figured out, thank you Gabriel, I spaced the holes correctly apart. Then from the bottom of the barrel, I measured up about 160 mil. This is the top of the spacer, or the false bottom. The reason that I measured this was because I had to know the absolute top travel. This is because if I was to put the float valve too high, the float valve would never reach the top of its travel on the arm. And what would happen? It would just continue to fill, it would overfill, and you would end up with ruined substrate and water everywhere. Measuring all this out on a template is a lot easier than doing it inside or outside of a barrel. With the body portion of the worldless bulkhead adapter, I took it so the crest of the nut was pointing to the bottom of the spacer gap. This way, when I went and did the nut up, I would be doing it up with 5 millimeters clearance. You can see that this would be a problem if you made it flush to the bottom of the barrel, and you'll see why when we come to actually fit it. I then just found the approximate middle and drew a circle. Next up was the most important bit, which was the float valve. I had to make sure that the float valve didn't max travel, otherwise it wouldn't shut off, but I also had to make sure that the float valve had sufficient spacing to fill enough water in so it covered the element. Not much of a challenge when you've planned it, and it's much easier to do on a template, however, still very important to get this right. It's much easier to do your first fit of the float valve above the element, this way that you can see the exit port of the valve is going to sufficiently cover the element. The element isn't actually the size of the nut and the housing that it sits in, but it's still a good idea to leave a reasonable gap. I think I left 50 millimeters between the top of the element and the exhaust port on the valve itself. I then did a few test swings holding the actual valve body as parallel to the line as I could. This way the float valve arm gave a true representation of where it would float rather than me just allowing it to bend. This is all back of the napkin maths, and so I left a big margin of error at the top, so it's probably about 3 or 4 centimeters gap between the top of the ball and the actual bottom of the spacer. However, better safe than sorry. It's probably worth talking about now that there are other designs out there for these sorts of barrels. There are even ones that have got like accessory boilers. There's ones that have got sauna elements that blow into them. There's lots of different kinds. However, for me, this is something I know. This is something I've worked with, and it's something that's worked for me for a long time. So I went with what I knew rather than just wasting money or spending money experimenting again. I simply repeated the process again with a drain valve, making it as close to the bottom spacer line as I could, but not quite on the bottom of the barrel. Again, you'll see why a bit later on, but it's worth the margin of error, at least initially. I then center punched the holes of the center of the holes where the element, float valve and drain would be. And then I took the template and I slaved it in position with the bottom of the paper about the same height as the bottom of the barrel. It can drop into the seam of the barrel where it's welded. Just bear that in mind, you'll lose your margin of error if you do that. So make sure it's as level as you can with the bottom of the barrel. Then just using a Sharpie or something that you can recognize, put your mark where your holes are, and that is the template transfer complete. Then simply center punch from the inside out and drill a pilot hole. Once you've got a pilot hole from the inside out, you can open it up to the right size. There's lots of ways to drill holes. You can chain drill, you can use a cone drill, you can use a bimetal hole saw. I use a Q-Max metal knockout punch. These are great bits of kit, and you can Google it or you can check the affiliate link below to figure out what they do. In my experience, it leaves a much cleaner hole than a hole saw or a cone drill or anything like that. Fitting the body portion of the bulkhead adapter couldn't really be any easier. Simply take the male side, pass it through with the washer on the outside, with the O-ring on the outside, and then tighten the nut down onto it from the inside. It's a little bit fiddly and you got to have long arms or a long set of Stilsons or something like that to hold it, but it does work better with two people for sure. I then did the same thing with the drain, making sure that the elbow was pointing downwards, and then attached it to the barrel with the hardware that I had knocking around. I then attached a ball valve to the drain. This meant I had control over the flow, and it also enabled me to attach a hose pipe to it to drain it out of the garage. I won't go into vast detail about how I wired the element. This is because I'm not an electrician, so I don't want to give you bad advice, but also because it's pretty self-explanatory. There's an earth, a live and a neutral. You can pretty much figure out where they go. Because the element has quite a lot of current being drawn through it, I used some RO7N cable, I think it was called, and I went to a 3-pin 16 amp plug. Again, probably a bit overkill, but UK Spurs are only rated to about 15 amps and 3000 watts, so this would have been well over it, and especially for the length of time these things run, it's much better to be safe than sorry. I then took the lid and drilled a hole in the middle. This is for the steam spacer that I was on about earlier. As you can see, there's lots of little holes for the steam to escape through. What I'm going to do here is put some standoffs on there, and then that way the steam can vent, flow and ebb around the holes, around the edge of the spacer, and it's much safer than a simple exhaust hole. The barrel lid had two rather large BSP threads already tapped into it, so I thought I'd take advantage of them. One what I used for the exhaust. I used a 2-inch to 3/4 inch BSP reducing bush, and that was for the ball valve that I used as the steam vent. Obviously the ball valve allowed me to have a bit of back pressure, but it also gave me the option of attaching a longer exhaust to it so I could vent out of the garage rather than into the garage. And then for the other attachment, all I had was a 1-inch to 1/2 inch BSP reducer, and I then attached an NPT 1/2 inch to that bush, which held the temperature probe. NPT and BSP aren't exactly the same, but they're almost the same. But when you connect them, for low pressure environments at least, you've got to use a fair bit of PTFE tape to pack them out. Attaching a tri-clamp couldn't be easier. Just put a gasket in between the two mating faces and tighten down the clamp, and that's it. You're done. You have a waterproof seal that's very easy to take out, very easy to clean, and very easy to upgrade. UK mains pressure is about 15 to 20 psi, so I had to attach a pressure reducing valve for the water. I also used a metal pipe to stand off the barrel from the hose pipe. That way the hose pipe didn't warp under the heat that was radiating. There's a lot more information on my website, but as you can see here, the barrel chunters along quite nicely between 80 and 90 degrees, and that was about an hour to get to about 95 degrees. So it's pretty hardcore, pretty heavy, and works great with the PID controller. I've ran it a few times now, and I'm absolutely over the moon with it. I'm really glad that I invested in stainless steel. It's a very, very expensive thing to do, and it's a very daunting thing to drill holes in your very expensive barrel, but it's worth every penny. You don't have to deal with any maintenance. All you have to do is clean it out at the end of the day and put it to bed. I know this was a long video, but I really hope it helps you avoid some of the mistakes I made when I first built my barrels. If you like the video, please consider subscribing to the channel. Better off heading over to my blog. I tend to update that a lot more regularly than I do my YouTube channel. There's lots more information over there that's on my YouTube channel, and there's also much more detailed write-ups of the projects that I have done in the past. Thank you very much for watching. Bye.